All right, so this is going to cover the introduction to circular motion. We're going to start with this hockey demo from CK12, where we're going to look at the direction of motion, the direction of the net force, and the resulting motion. And we're going to see what do we need to do in order to move the object in a circle? How do we need to apply that net force? So here I have this hockey player that I can rotate the force he's applying. That gray vector is the force he's applying. And we're going to consider this to be a frictionless surface. So the force from the hockey player is really going to represent the net force, right? The net force in the x direction. So currently that red vector represents my velocity. As you can see, the puck is moving at 6 meters a second right now. So if I push if I apply a force in the same direction as the velocity, right, just a quick force, it looks like I'm now still moving to the right, but I have increased my velocity. So you can see I failed at trying to move this in a circle, but I'm gonna add that to my table, right? I have a rightward velocity, which is the direction of motion. I have a rightward net force, and this object has sped up rightward. So now let's see, okay, retry, right? There's my velocity, my puck coming in. Now let's try opposite. So I'm gonna apply a net force opposite the direction of motion. Oops, oh no. And I'm now moving with a velocity of 3.8 meters a second, but still to the right. So I have rightward velocity or direction of motion, leftward net force, and I have slowed down is what I was just trying to slow down. All right, so clearly left and right alone won't work. So maybe if I try to push it like sort of like that, maybe that'll get it to sort of, right? I want it to go in a circle, so maybe I push it that way. But that's still, it didn't follow the path, right? So I sped up and I changed my direction a little bit. So it's going to the right, and my direction of the net force was kind of like up and right, and I sped up and I had a slight turn, slight direction change. Okay, so maybe that upward velocity, I just have to let me retry this. Maybe I just have to apply more upward. So let's try all the way upward, right? Let's just really go for it. Boom. Oh, that gets it. Okay, that was pretty good. So maybe if I try, let's see if I can just continue to apply upward. Will that have me, I mean, this is looking pretty good, right? So that green arrow is showing me my last net force relative to the velocity. So like that's kind of like directly upward now, which I guess we could kind of define as perpendicular. So this is looking pretty promising. All right. So I'm seeing that if I have a rightward velocity and an upward force, right? And my velocity is increasing a little bit, but I think that's because I'm not doing a very good job of positioning him perfectly upward. I think I'm doing a little bit rightward as well. But this is where I really start to turn. So what this is showing me is that in order to get something to move in a circle, sorry for the Amazon pop-up, I need to apply a force, right? These two are 90 degrees apart, so to speak. So that's also known as perpendicular. So I need to apply a force perpendicular to the direction of motion. So in order to move that puck in a circle, I had to apply a constant net force, and I had to apply it perpendicular to the velocity. And if I was better at doing it, I would see that the puck travels at a constant speed. And I'm being very cautious about the fact that I'm calling it a constant speed and not a constant velocity, because you might be asking, why is there a net force if we're not speeding up or slowing down? So the thing to remember is that acceleration is defined as a change in velocity over time. And velocity is a vector quantity, which means it has a magnitude or an amount and a direction. So if we want to change the velocity, we can either change the magnitude by speeding up or slowing down, or change the direction we're moving. And when we apply that force perpendicular, that's exactly what we're doing. We're changing the direction of motion. So that's how we're accelerating, even though we're not speeding up or slowing down. Now you might be thinking, well, we know that the net force equation is F equals ma, and we've previously defined A as a change in velocity over time, where there's some sort of number here. But if we're moving at that constant speed, and I can say constant speed because speed is a scalar quantity and has no direction, so that's why I was cautious to say constant speed here. Okay? If I'm moving at a constant speed, my change in speed is 0. So how do I define acceleration? And what ends up happening is we now have a new acceleration equation for objects moving in a circle at a constant speed. This is called the centripetal acceleration, right? Abbreviated A with a subscript of c, and it's equal to the speed squared over the radius. Okay? The centripetal acceleration is still an acceleration measured in meters per second squared. Speed is measured in meters per second, and radius in meters. Okay? The word centripetal comes from Latin, and it means center seeking. So we know that that acceleration has to point towards the center because the net force has to point towards the center. So that's why we call it the center seeking acceleration. I think it also sounds like center pole. Now, if we're curious about where that equation comes from, I'm going to play a video now about how to get that equation. If you do not care and you just are happy knowing that that equation is what it is, then you can skip the next 4 minutes of this video.
Let's have an object moving along a circular arc of radius r. It's fundamental angular displacement of theta. And let's find the velocity at this and this position, v1 and v2. Let's draw a vector triangle involving v1 and v2. Now, what does this side of the triangle represent? It represents the change in velocity delta v. See, the original velocity plus the change in velocity is equal to the final velocity. You'll see that this angle here is actually the same angle in value. See, r and r forms the angle theta. So v1 and v2 should also form the angle theta, because v1 and v2 are just these two arcs 90 degrees. Let's draw another triangle based on r and r. Of course, this angle here will be theta. So what should this triangle correspond to? Now look here. This arc length should be exactly equal to v delta t. So delta t is the amount of time, and then the object to go from here to here. And v is just the speed. V is the same as v1, is the same as v2, because this is the constant speed. So the arc length is v delta t. If theta is very small, then the arc length is practically the same length as the line joining these two positions. Okay? However, arc length and the straight line joining these two lines are practically the same if theta is small enough. So the third side of the triangle here is basically equal to the arc length, which is v delta t. So subsidies are doing the same thing. Are we cheating? Because the two lines are not exactly the same length. by V1 should be equals to the ratio of the corresponding sides on the other triangle, which is V delta T divided by R. Rearrange the equation, you get delta T over delta T is equals to V squared over R. Where delta T is not enough, delta T over delta T is actually instantaneous acceleration, which is V squared over R. So, with some simple geometry, we have shown that when an object is doing circular motion, it's a constant speed V, radius R, and its velocity is changing at the rate of V squared over R. That's all.
All right, so that's where that V squared over R equation comes from, if you were ever curious about why it is that way. And it looks like this video is just going to follow the screen until I get rid of it. There we go. Okay, so that means then if our net force, we know net force is, right, from Newton's second law, we need net force is ma. So for an object moving in a circle, the net force is really mass times that centripetal acceleration, or mv squared over r. And we give this a special name. We call it the centripetal, that same center seeking, center pulling force, okay? And the fact that it's a centripetal force gives you an idea of what direction that net force needs to be in, okay? Now, again, this is a net force, so it's not the force that's actually acting, it's just a combination of the forces acting on an object, okay? So this centripetal force does not add a new net force to our systems, but rather replaces the net force in the x direction or the net force in the y direction. So we're either doing a horizontal circle or a vertical circle. And that's where we, instead of, if we're doing a horizontal circle, we would replace the net force in the x direction with net force or centripetal force. If we're doing a vertical circle, then we're going to replace the net force in the y direction with a centripetal force. So let's do a quick example. Let's say we have this object, right, this ball with mass 1 kilogram, and it is connected to some arm that has a radius of 1 meter, and that arm is connected to some motor that spins this ball in a circle on top of a frictionless surface at a nice constant speed, right? And it does so that we do one rotation or one revolution in 30 seconds. Now, I labeled this as a T, 30 seconds, but this might also be called the period, right? The period is just the time to complete one cycle, okay? So the time to go around the circle once is 30 seconds, so I could also say that the period here is 30 seconds. So we want to know what force must the arm exert on the ball to keep it moving at a constant speed in a circle. So I'm going to draw a kind of like a side view. Like if I crouched down and looked at this ball from the side, right, I would have, of course, a force of gravity and a normal force, and then there'd be some sort of like applied force from that arm, or a tension force. Since this ball is rotating horizontally on this circle, I should have said that this is a top view. Okay. I know that the net force in the x direction is instead going to replace with a centripetal force, so must equal MAC. Now, vertically, this ball is not moving at all, so the net force in the y direction is still going to be 0, which still tells me that my normal force equals the force of gravity like I'm used to. So in the x direction, the only force that's acting horizontally is that tension force. So that's the force that I'm looking for. So in order to do that, I need to calculate mass times centripetal acceleration. I'm not given the centripetal acceleration at all, but I am given the mass, so I'm going to keep n. And then I know that AC, the centripetal acceleration, is v squared over the radius. Now you might be wondering, should I do a big R or a little r? It doesn't matter. I usually do a big R because sometimes my little r's, if I draw them too fast, look like V's. So just for clarity, I use a big R. If you like little r's, that's fine too. Okay. So V squared over R, remember V is the speed that I'm moving at, the constant speed. But I'm not given that, right? I don't know how fast I'm going. I have the radius, but I don't have the speed. So that tells me I might need to calculate that constant speed. Okay. Now, if we think back to kinematics, the speed of something, and again, speed, right? So speed was based off of distance over the time, okay? Now, when we were calculating speeds, we were talking straight line distances, but this object is still moving a distance, right? It's still moving a distance as it goes around this circle. So I need to figure out what is this distance around a circle. And that distance around a circle has a very special name. If you think back to geometry, it's called the circumference, right? That's the distance around the circle. And we already talked about how the time to go around a circle is called the period. So I can find the speed by doing the circumference over the period. Well, how do I find circumference? I gotta do 2 pi r, 2 pi times the radius. So over the period, and period is represented with a capital T, right? Which is why I usually get in the habit of writing my tensions as an FT and not just a T. All right, so this speed has got to be 2 pi times 1 meter over 30 seconds. So I can do that in my calculator. 2 pi times 1 over 30 gives me 0.21. And it's a speed, so still in meters per second. All right, so now I can go back and I have all the information I need to fill into this mv squared over r. My m was 1 kilogram. My speed we just found was 0.21 meters per second. And we're not going to forget to square it. I will say forgetting the squared here is one of the most common algebra errors. And then I divide by the radius, which is 1 meter. So 0.21 squared, nope, 0.21. So that gives me a force of 0.04 newtons. And it's still newtons, right? We're still dealing with forces. So the units are still the same for everything that we're dealing with. So that's an example of how we deal with circular motion. So to recap, when something is moving in a circle, we need a net force in order for that thing to move to a circle, and that net force must be perpendicular to the velocity. We know we have a net force, and we know we're accelerating because it's the direction that's changing, okay? And that is part of what we could have for acceleration. Okay? We then defined a new acceleration for moving at a constant speed but changing direction, right? The centripetal acceleration, or for the acceleration for something moving in a circle, is v squared, which is the speed, over the radius. So then the net force for something moving in a circle, aka the centripetal force, is the net force equals MAC, and that net force replaces the horizontal or vertical net force, depending upon what kind of circle we are doing. And that's the basics of circular motion.